Method of sections. WME. Copyright statement. This 172.24.1. Contents. Truss analysis. Used to determine the loadings within a body. If a body is in equilibrium, any part of the body is in equilibrium. To find forces within members, an imaginary section is used to cut each member into two and expose each internal force as external. The method of sections. Truss analysis. Points of 3G form a simply supported truss with a pin at point G and a roller at point E. Loads P1, P2, and P3. When the force in only one member or the forces in a very few members are desired, the method of sections works well. To determine the force in member BD, form a section by cutting the truss at NN and create a free body diagram for the left side. An FBD could have been created for the right side, but why is this a less desirable choice? Think and discuss. Points of 3G form a simply supported truss with a pin at point G and a roller at point E. Loads P1. Truss analysis. Points of 3G form a simply supported truss with a. The section is created by making a vertical cut through members BD, B, and CE. The member forces FBD, FBE, and FC. Notice that the exposed internal forces are all assumed to be in tension. Cut KK is through members BD, B, BC, and AC. Cut PP is through members A. Notice that any cut may be chosen, so long as the cut creates a separated section. So, for example, this cut with line PP is acceptable. Truss analysis. Method of sections. Truss is made of several simple trusses. ABC is a truss in the shape of a triangle. Point A at the bottom left and point C at the ABC is a. This truss contains a redundant member and is therefore statically indeterminate, making M greater than 2n minus 3. Truss is made of several simple trusses. ABC is a truss in the shape. ABC is a rigid. M plus 4 equals 2n. Additional reaction forces may be necessary to make the truss rigid. Necessary but insufficient condition for a compound truss to be statically determinate, rigid, and completely constrained. M plus R equals 2n. Points of through L form a simply supported truss with a pin at point A and a roller. Points of through L form a simply supported truss with a pin at point A. 1. Draw the FBD for the entire truss. Apply the equilibrium conditions and solve for the reactions at A and L. 2. Make a cut through members FH, GH, and GI and take the right-hand section as a free body. The left side would also be acceptable. 3. Apply the conditions for static equilibrium to determine the desired member forces. Free body diagram of truss. Free body diagram using section NN. Member forces FFH, FGH, and FGI are exposed. What is the one equilibrium equation that can be solved to find FGI? Confirm your answer with a neighbor. Sum of the moments about point H. Cap F sub cap G cap I equals 13.13 kilonewtons cap T. FFGGG equals 13. Cap F sub cap F cap H equals 13.81 kilonewtons cap. FFFFH equals 13.8. There are many options for finding FGH at this point. Here's one more. Cap F sub cap G cap H equals 1.371 kilonewtons cap C. FFGGH equals 1.371 kilonewtons CC. Sample problem 1. Reflect and think. Sometimes you should resolve a force into components to include it in the equilibrium equations. By first sliding this force along its line of action to a more strategic point, you might eliminate one of its components from a moment equilibrium equation. 17. Office Faculty Department. The method of joints is usually the best method to use when you need to find the forces in all of the members of a simple truss. The method of sections is more efficient when you need to find the force in only one member or the forces in a very few members of a simple truss. The method of sections also must be used when the truss is not a simple truss. To determine the force in a given truss member by the method of sections. 1. Draw a free body diagram of the entire truss and determine reactions of the supports. 2. Pass a section through 3 members only of the truss, one of which is the member whose force you want to find. 3. Select one of these two portions of truss and draw its free body diagram. 4. You can now write 3 equilibrium equations that can be solved for the forces in the 3 intersected members. There are special cases where you can cut more than 3 members if you can make equations that solve directly for a member.
In this video, we are going to introduce another method for simple truss analysis, the method of sections. Once again, for any truss member that is either in tension or compression, if we run an imaginary cut through it, the internal force can be imagined to have been exposed, and it can be considered as external. So now we have a way to apply rigid body equilibrium method to analyze the internal reaction. We will learn more about the internal reactions later. Since, if you recall, one 3D rigid body free body diagram enables us to solve for a maximum of 3 unknowns. So if we only need to solve for the forces in no more than 3 truss members in the structure, we can imaginarily cut the structure open and apply rigid body equilibrium analysis. This is known as the method of sections. Let's look at this example. For this structure, we are not asked to solve for all members, just BC, CF, and CG. Therefore, instead of using the method of joints, we use the method of sections because this way there's fewer steps involved. Here's the plan. Since we need to solve for the forces in members BC, CF, and CG, we can run an imaginary cut through these 3 members. And now the internal forces in these 3 members are exposed. Note how there are actions and reactions on the left and right segment. So we can choose either side for the calculation and we will get the same results. Don't forget, we can only solve for 3 unknowns using one rigid body free body diagram. Therefore, either side we choose, we need to determine the support reaction first. Now, the left segment has only one support reaction associated with the roller, while the right segment has 2 support reactions associated with the ping. So for convenience, we should pick the left segment for further analysis. So the first step for this problem, it is necessary to determine the support reaction at point A. To do so, we draw the free body diagram for the entire structure and summarize the resultant moment about point D. And from this single equation, we are able to solve for the force AY. Keep in mind that for some problems, it might not be necessary to determine the support reaction, so you should use your own judgment. Step 2, cut the structure, and we have already decided to choose the left segment for our analysis. Step 3, apply rigid body equilibrium to solve for our unknowns. We start with a free body diagram of the left segment, and since we have already solved for the support reaction at point A, we have only 3 unknowns, FBC, FCF, and FFG, and we can write 3 equilibrium equations. Remember, normally we would write 2 force equations and 1 moment equation. However, note that how force BC and force CF are concurrent, and force CF and force FG are also concurrent. Therefore, it will be convenient to write 2 moment equilibrium equations about point C and point F. See, when the moment is summarized about point F, only FBC shows up and you can solve it easily from this equation. And when moment is summarized about point C, you only have force FG and can easily solve it as well. Lastly, let's write 1 force equilibrium equation along the x direction, and from it we can solve for FCF. Hopefully from this example, you have learned how to apply the method of sections for your simple truss analysis. We actually have already learned a little bit about the internal forces when we studied the simple truss analysis. For a truss member with forces acting on it, the member could be in tension or compression. And although the forces only act on the two ends, force must also develop inside the member because we should be able to run an imaginary cut at any place through the member. And each segment must also be in force equilibrium according to Newton's first law. These forces are internal forces. They are exerted by the neighboring materials to keep the segments from falling. This is a very simple example of internal forces, and we are about to learn more complicated cases. But before doing that, let's take a moment and think why we are interested in learning about internal forces. You've probably come to this answer. We want to know the internal force so we can make sure it does not exceed what the material can withstand. We don't want the members to fail under the loadings. Actually, it is not the force that matters, because we can simply use a thicker, bigger member, and that seems to fix the problem. It is the force over unit area, stress, that cannot exceed a certain value. The stress associated with the internal normal force, like the ones in the truss members, is normal stress, sigma, which is calculated as F over the cross-sectional area of the member, A, and it should not be greater than an allowable value. As you can probably tell, this is beyond the current statics class, but it is always good to know why you are learning what you learn. Now let's look at a more general example. In this example, we have a cantilever beam. Point A is a fixed support, and we're asked to find the internal forces at point B. Since we're asked to solve for internal forces, we need to first expose those forces, make them external, and then we can draw the free body diagram and apply rigid body equilibrium analysis that we have already learned. In fact, we are not unfamiliar with this approach since we used it to solve for truss forces already. And this method is called the method of sections. Now let's look at the proper procedures when applying the method of sections. First step, determine the external support reactions and complete the free body diagram of the entire member if necessary. Of course, sometimes it is not necessary to do so, and you will be able to tell afterwards. But for now, let's just solve them. Since at point A we have a fixed support, there are 3 support reactions, 2 forces, and a couple moments, and we can solve for all of them by applying the rigid body equilibrium analysis. Step 2, cut the member at the specified point, and in this case, point B. And we separate the 2 parts, and now we need to specify what kinds of unknown reactions we should draw at the cut. Let's look at the right segment. It is being held by the left segment, and it is not allowed to move horizontally, or vertically, or rotate. That sounds just like a fixed support. In fact, don't forget in this class, we assume all members that we study are non-deformable. Therefore, any portion of any member can be considered to be held by an imaginary fixed support. So let's draw the same unknown reactions as a fixed support. 2 force reactions and 1 couple moment reaction. And because of actions and reactions, we can also draw the unknown reactions on the left segment. They have the same magnitudes but opposite directions as the ones on the right. And therefore, we only need to solve for one set of the unknown reactions, either from the left segment or from the right segment. So step 3 is to choose one side and solve for the unknowns. I will demonstrate calculations using both sides just to show that they will lead to the same answers. But when you make your own pick, of course you want to choose the side that makes the calculation easier. In this case, you should pick the right side so you don't need to solve for the support reactions in the first place. So we put the left segment in our appropriate coordinate system, write the 3 two-dimensional rigid body equilibrium equations, force along the x direction, force along the y direction, and a couple moments about point B, and we can solve for all 3 unknowns. And we can do the same thing for the right segment and get exactly the same answers. Note that we want to summarize the total moment about point B because this way the unknowns VB and MB would not cause any moment about point B, therefore they do not show up in your moment equilibrium equation. Now, let's look at these names. The first one is normal force because it is normal or perpendicular to the cross-section of the member. We are already familiar with this one because all the forces we solved for simple truss analysis are normal forces. The second one, V, is shear force, and it is always tangent to the cross-section. The third one is the bending moment, and as you can tell, it causes a bending tendency in the member. Although you can define the positive directions of these internal forces whichever way you want, there are a set of sign conventions. The purpose is for better communication between engineers, so other engineers can quickly interpret your calculations. According to the sign conventions, for a 2D problem, the normal force is considered to be positive if it's tensile. The shear force is considered to be positive if it creates a clockwise rotational effect on the segment. And the bending moment is considered to be positive if it creates a concave upwards bending effect on the segment. I would suggest you always draw your unknown internal forces according to the sign convention to avoid confusion. Now let's quickly look at another example. Determine the internal forces at point C. Again, we are going to apply the method of sections. First, let's choose the side we want to solve. In this example, we inevitably have to solve for some external support reactions first. But at point A, we have a roller support, which only has 1 support reaction, versus at point B, we have a pin support with 2 support reactions. Therefore, we choose the left side with the roller support. So we solve for force Fa at the roller support using 1 moment equilibrium equation. And now we run an imaginary cut through point C and analyze the left segment. We draw the 3 internal forces according to the sign convention: the normal force, the shear force, and the bending moment. We need to replace the distributed load by an equivalent concentrated load. Now we set up the rigid body equilibrium equations, and we can solve for all 3 unknowns. What if you have a 3-dimensional problem? For example, for this beam that is subjected to the external forces as shown, what are the internal forces at point C in this beam? Well, we can solve the problem using the same method of sections, following the same procedures as described for the 2D problems. We run an imaginary cut through point C, separate the 2 parts, pick one side to solve, determine the support external reactions if necessary, put the segment in an appropriate coordinate system, draw the unknown internal reactions the same way for a fixed support, and solve for all unknowns by applying the 3-dimensional rigid body equilibrium equations. Keep in mind that for 3D problems, there are no sign conventions like the ones we had for 2D problems. Therefore, the signs for the internal reactions will depend on how you set up your coordinate system. Let's say we choose the left segment, and these are the 6 internal reactions, and you can solve for all of them by applying the 6 rigid body equilibrium equations. Now you have 1 normal force that is along the axial direction, and it's perpendicular to the cross-section. You have 2 shear forces that are tangent to the cross-section, 2 bending moments, and also you have 1 torsional moment that creates a twisting effect of the member. As you will learn in the class of mechanics of materials, these different internal forces will cause different types of stresses and deformations and even failures in the members. In the previous video, we learned how to determine the internal forces at a specified location on a member. However, we would rather know where the maximum internal reaction happens in the member, because that's where the member is most likely to fail. And in most cases, we cannot easily tell that location. We actually have already learned a little bit about the internal forces when we studied the simple truss analysis. For a truss member with forces acting on it, the member could be in tension or compression. And although the forces only act on the two ends,
Frames and machines. Wmec-Civ. Copyright. Contents. Application. https:/application. https:// Charlie and mechanic on top of machinery. Max Monotry. No fear closure in Swift 4 with Bob the developer. Introduction. A. Trusses, formed from two force members, i.e., straight members with endpoint connections and forces that act only at these endpoints. Introduction. B. Frames, contain at least one multi-force member, i.e., member acted upon by three or more forces. Introduction. Analysis of a frame. A free body diagram of the complete frame is used to determine the external forces acting on the frame. Internal forces are determined by dismembering the frame and creating free body diagrams for each component. Analysis of a frame. Forces on multiforce members have unknown magnitude and line of action. They must be represented with two unknown components. Forces between connected components are equal, have the same line of action, and opposite sense. Frames that collapse without supports. The frame is supported by a pin at points A and B. Vertical loads B and Q are applied members AC and BC. The frame is supported by a pin at points A and B. Vertical loads B and Q are applied members AC and BC. Point B is to the right of point A. A free body diagram of the complete frame indicates four unknown force components, which cannot be completely determined from the three available equilibrium conditions for this FBD. Free body diagram of the frame. The frame must be considered as two distinct, but related, rigid bodies. Frames that collapse without supports. Equilibrium requirements for the two rigid bodies yield 6 independent equations. Thus, taking the frame apart made the problem solvable. Free body diagram of the frame. The frame is supported by a pin at point A and roller at point B. A 480 Newton. Members AC and BCD are connected by a pin at C and by the link D. For the loading shown, determine the force in link D and the components of the force exerted at C on member BCD. The frame is supported by a pin at point A and roller at point B. A 480 strategy. Follow the general procedure discussed in this section. First, treat the entire frame as a free body, which will enable you to find the reactions at A and B. Then dismember the frame and treat each member as a free body, which will give you the equations needed to find the force at C. Free body diagram of the frame. Modeling and analysis. Create a free body diagram for the complete frame and solve for the support reactions. Free body diagram of the frame. AAYY, cap B equals 300 and goes, BB equals 300, cap A sub X equals 300 and left arrow. AAXX equals 300 and left pointing arrow. Note, top figure, free body diagram of the frame. Create a free body diagram for member BCD since the problem asks for forces on this body. Choose the best FBD, then discuss your choice with a neighbor. Justify your choice. Top figure, free body diagram of the frame. Middle right figure, free body diagram of member BCD. Bottom left figure, free body diagram of member BCD. Bottom right figure, free body diagram of member BCD. A, B, C, D, free body diagram of member BCD. Using the best FBD for member BCD, what is the one equilibrium equation that can be used to directly determine FEE? Please discuss. Free body diagram of member BCD. Using the best FBD for member BCD, what is the one equilibrium equation that can be used to directly determine FEE? Please discuss. Free body diagram of member BCD. FFDDD equals 561 NCC. Sum of forces in the x and y directions may be used to find the force components at C. Cap C sub x equals minus 795 N. CCXX equals minus 795 N. Cap C sub y equals.
Balik check.
Free body diagram of member ACE and DE. Reflect and think. Check the computations by considering the free body ACE. Checks. Machines. An input forces P are applied to the handles and the output forces Q cut the wire in the jaws of the pliers. An input forces P are applied to the handles and the output forces Q cut the wire in the jaws of the pliers. Given the magnitude of P, determine the magnitude of Q. An input forces P are applied to the handles and the output forces Q cause a reaction against the jaws of the pliers. Create a free body diagram of the complete machine, including the reaction that the wire exerts. The machine is a non-rigid structure. Use one of the pieces as a free body. Discuss why the forces that are such as that shown. Some moments about A. Summary. Equilibrium equations applied to 1. Entire body. 2. Joints to method of joints. 3. Section to method of sections. 4. Members to frames and machines. 5. Pieces of members to internal forces. Internal forces and shear and bending moments. Wmec-Civ 10. Copyright. This material. Contents. Application. Introduction. Internal force in members. Internal forces in members. Internal forces in members. Crane made up of a vertical member ABCD, horizontal member CEF, and diagonal member B. Crane is supported by a pin at point A and cable at point. Crane made up. Internal forces in members. Shear force and bending moment. The frame is supported by a pin at point E and a roller at point F. Determine the internal forces. A in member ACF at point J and B in member BCD at K. The frame is supported by a pin at point E and a roller at point F. Strategy. Compute reactions and forces at connections for each member. Cut member ACF at J. The internal forces at J are represented by an equivalent force couple system that is determined by considering equilibrium of either. Cut member BCD at K. Determine the force couple system equivalent to internal forces at K by applying equilibrium conditions to either part. Modeling. Compute reactions and connection forces. Analysis. Consider entire frame as a free body and apply equilibrium conditions. FFYY equals 0 equals minus 2400 N. FFFF equals 180 FFFFYY. Free body diagram of member BCD. Dash. Why are forces at B and C drawn in these directions? Is there a choice on the directions? Why are there two force components at each point instead of just a single force? Think about these and discuss. Drawing the FBD for member. BCD. Drawing the FBD for member. Abe. Why are forces at B in these directions? Is there a choice on the directions? Why are there two force components at A instead of just a single force? Think about these and discuss. Finally, the FBD for member. ACF. Sample problem 7.1. Free body diagram of member BCD. Consider member BCD as a free body. MMCC equals 0 equals minus. Sum of cap M sub cap C equals 0 equals minus open paren 2400 N, close paren open paren 1.2 meters, close paren plus cap B sub Y, open paren 2.4 meters, close paren. FFXX equals 0 equals minus BBXX plus CCXX equals 0 rightwards double arrow BBXX equals CCXX. Sample problem 7.1. Consider member A as a free body. N area summation ffxx equals 0 equals bbxx minus aaxx equals 0 rightward from member BCD. Free body diagrams of portions AJ and FJ of member ACF. Cut member ACF at J. The internal forces at J are represented by an equivalent force couple system. Consider free body AJ. Free body diagrams of portions AJ and FJ of member ACF. M equals 2100. Cap F equals 1340. FF equals 13. Cap P equals 1197 N. VV equals 11. Free body diagrams of portions BK and DK of member B. Cut member BCD at K. Determine a force couple system equivalent to internal forces at K. Consider free body BK. Cap M equals minus 1800 N dot M. M equals minus 1800 N dot operator M. Free body diagrams of portions BK and DK of member BCD. Cap P, VV equals minus 1200 N. Reflect and think. Reflect and think. The mathematical techniques involved in solving a problem of this type are not new. They are simply applications of concepts presented in earlier chapters. However, the physical interpretation is new. We are now determining the internal forces and moments within a structural member. These are of central importance in the study of mechanics of materials. The mathematical techniques involved in solving a problem of this static friction. Wmec-Civ 1001 week 6 lesson 1 copyright. This material contents. Application. The laws of dry friction, coefficients of friction revision. Further increase in PP causes the block to begin to move, while FF drops to a smaller kinetic friction force FF. KK. Dot. FF. KK. Equals. MKK. NN. M. Bold italic cap F sub, bold italic M over bold italic K N subscript. Maximum static friction force and kinetic friction force are proportional to normal force, dependent on type and condition of contact surfaces, independent of contact area. Metal on metal. 0.15 minus 0.60. Metal on wood. 0.20 minus 0.60. Metal on stone. 0.30 minus 0.70. Metal on leather. 0. Wood on 0. Wood on leather. 0. Stone. 0. Earth on 0. Rubber. 0. Kinetic friction force. FF. KK. Equals. MKK. NN. No friction. PX equals 0. Block, with weight W, positioned on horizontal surface subject to force P, acting down. No friction. N equals P plus W. PX equals 0. Block, with weight W, positioned on horizontal surface subject to force P, acting down and to the right. No motion. PX less than F. F equals PX. F less than micro SN. N equals PY plus W. No motion. PX less than F. Block, with weight W, positioned on horizontal surface subject to force P, acting down. No friction. N equals P plus W. PX equals 0. Motion impending. PX equals FM. Block, with weight W, positioned on horizontal surface subject to force P, acting down and to the right. No motion. PX less than F. F equals PX. F less than micro SN. N equals PY plus W. Motion. PX greater than FM, or motion already occurring. The laws of dry friction, angles of friction. Block, with weight W, positioned on horizontal surface subject to force P, acting down. No friction. R equals N. Block, with weight W, positioned on horizontal surface subject to force P, acting down and to the right. No motion. F equals PX. Phi less than phi S. Reaction R acting up and to the left. No motion. Block, with weight W, positioned on horizontal surface subject to force P, acting down. No friction. R equals N. Motion impending. Block, with weight W, positioned on horizontal surface subject to force P, acting down and to the right. No motion. F equals PX. Phi less than phi S. Reaction R acting up and to the left. Motion. The laws of dry friction, angles of friction. Block, with weight W, positioned on horizontal surface. No friction. Theta equals 0. Block, with weight W, positioned on inclined surface. No motion. Phi less than phi S. N equals W cos theta. F equals W sin theta. No motion. Block, with weight W, positioned on horizontal surface. No friction. Theta equals 0. Motion impending. Block, with weight W, positioned on inclined surface. No motion. Phi less than phi S. N equals W cos theta. F equals W sin theta. Motion. Problems involving dry friction. All applied forces known. Motion is impending. Determine value of coefficient of static friction. 300-pound block is positioned on an incline with a slope of 3/4. 100-pound force acting up the plane is applied to the block. N. 300-pound block is positioned on an incline with a slope of 3/4. 100-pound force acting up the plane is applied to the block. N. 300-pound block is positioned on an incline with a slope of 3/4. 100-pound force acting up the plane is applied to the block. Strategy. Draw the free body diagram for the block. Remember that the friction force is opposite the direction of impending motion. Determine values of friction force and normal reaction force from plane required to maintain equilibrium. Calculate maximum friction force and compare with friction force required for equilibrium. If it is greater, block will not slide. If maximum friction force is less than friction force required for equilibrium, block will slide. Calculate kinetic friction force. 300-pound block is positioned on an incline with a slope of 3/4. 100-pound force acting up the plane is applied to the block. N. Free body diagram showing applied 100-pound, weight force, normal force, friction force acting down the plane. What does the sign tell you about the assumed direction of impending motion? Think about this and discuss with a neighbor. Free body diagram showing applied 100-pound, weight force, normal force, friction force acting down the plane. N. What does this solution imply about the block? Discuss this with a neighbor. Free body diagram showing applied 100-pound, weight force, normal force, friction force acting down the plane. N. What does this solution imply about the block? Discuss this with a neighbor. The block will slide down the plane. Free body diagram showing applied 100-pound, weight force, normal, N. Free body diagram showing applied 100, factual equals 48 N. Free body diagram showing applied 100-pound, weight force, normal force, friction force F equals 48 pounds acting up the plane. N. Sample problem 8.1. Reflect and think. This is a typical friction problem of the first type. Note that you use the coefficient of static friction to determine if the crate moves, but once you found that it does move, you needed the coefficient of kinetic friction to determine the friction force. 17. Office faculty department. The bracket slides on two 3-inch diameter collars, one at the top of the bracket and one at the bottom. The load W, acting down, is applied to the bracket at distance x from the center of the pipe. Cm. The bracket slides on two 3-inch diameter collars, one at the top of the bracket and one at the bottom. The The load W, acting down, is applied to the bracket at distance x from the center of the pipe. Cm. Draw a free body diagram of the body under study bracket. Apply conditions for static equilibrium to find minimum x. The bracket slides on two 3-inch diameter collars, one at the top of the bracket and one at the bottom. The load W, acting down, is applied to the bracket at distance x from the center of the pipe. Cm. Free body diagram of bracket. Fa, and now are applied to point A. Cm. Free body diagram of bracket. Fa, and now are applied to point A. F flat are applied to point B. The force W is applied 1.5 inches from the center of the collar. Cm. NNDB equals naught. NNAA equals NNDB equals 2 WW. X equals 12 centimeters. Rectangle. XX equals 12 centimeters. Note that it doesn't matter what W is. Does this make sense? Free body diagram of bracket. Fa, and now are applied to point A. F flat are applied to point B. The force W is applied 1.5 inches from the center of the collar. Cm. Sample problem 8.3. Reflect and think. In a problem like this, you may not figure out how to approach the solution until you draw the free body diagram and examine what information you were given and what you need to find. In this case, since you were asked to find a distance, the need to evaluate moment equilibrium should be clear. 22. Office Faculty Department. Wedges. Free body diagram of wedges. Free body diagram of block is showing the weight force W, friction and normal forces from the wall, F1 and N1, as well as friction and normal forces from the wedge C, F2 and N2. Wedges. Free body diagram of wedge C showing friction and normal forces from block A, F2 and N2, friction and normal forces from the wedge D, F3 and N3, as well as force B. Square threaded screws. A block is positioned on an inclined plane. Force Q is applied to the block. The weight force, W, is shown. The reaction from the plane, R, acts up and to the left. Moment of force Q is equal to moment of force P. Q equals Pa R. A block is positioned on an inclined plane. Force Q is applied to the block. The weight force, W, is shown. The reaction from the plane, R, acts up and to the right at an angle phi s theta left of vertical. Phi s greater than theta. Self-locking, solve for Q to lower load. A block is positioned on an inclined plane. Force Q is applied to the block. The weight force, W, is shown. The reaction from the plane, R, acts up and to the left. Phi s greater than theta. Non-locking, solve for Q to hold load. Using a block and plane analogy with impending motion up the plane, calculate the clamping force with a force triangle. Reflecting impending motion down the plane, calculate the force and couple required to loosen the clamp. Free body diagram of the block. Force triangle with forces W, Q, and R. Tan. Force triangle with forces W, Q, and R. Cap W equals 17.97 kilonewtons. Rectangle. Free body diagram of the block. QQ equals 2.975 kilonewtons. Sample problem 8.6. Reflect and think. In practice, you often have to determine the force effectively acting on a screw by setting the moment of that force about the axis of the screw equal to an applied couple. However, the rest of the analysis is mostly an application of dry friction. Also note that the couple required to loosen a screw is not the same as the couple required to tighten it. 32. Office Faculty Department.
If you're currently a
Welcome to Lecture Online. One of the practical applications of the concept of a wedge is when you look at screws, and in this case we're looking at what we call a square threaded screw. What we're trying to do is we're trying to turn it counterclockwise so that the screw will come out. So we have pending motion upward. And the way we look at it is that the screw will have a certain amount of weight pushing down. That could be because it's holding something down or simply using the weight of the screw. We're going to push against it like here at the edge of the angle at a distance r away from the center of the screw. So this is the moment arm, this is the force applied, Fp, such that the force applied to the thread itself can be found by taking F of P and multiplying times the ratio of the moment arm of the applied force divided by the radius of the screw itself, the mean radius of where the thread touches the object in which it's screwed. So you can see that large r is much larger than the small r, so the force applied to the screw is very large due to the moment arm right here. So when we take a look at what happens at the thread itself, we can imagine this being the thread of the screw pushing against the object, which of course also is threaded. And so if we're pushing against the screw so that the screw will wind itself upward, we can see that the thread of the screw will be pushing against the thread of the object that it's embedded in. So the reactionary force will go in this way, which is the sum of the normal force plus the friction force. And again, if you know the coefficient of friction, and in this case, since nothing is moving, we're talking about pending motion upward, we take the static coefficient of friction, and the angle phi is equal to the arctangent of the static coefficient of friction, such that the angle of the reactionary force and the vertical will be the sum of the angle made by the thread, which is called the lead angle, and the angle phi, which is caused by the coefficient of static friction. You must add those two angles together. Notice that this here represents the distance of one complete rotation of the thread, which is 2 pi times r, small r being the radius, the mean radius of the thread. So this is imagined to be the entire distance of one time around the screw, so to speak. And so then you can see that the thread will work its way up, or the screw will work its way up the thread. That's how you want to take a look at it. So we have the weight of the screw, the force applied to make the screw go upward, which is caused by the force here on the handle. And then we have the reactionary force. Now when we take those three forces together, since nothing is moving yet, we're at pending motion upward, we can add the three forces together in a triangle like that, and of course they must add up to 0. So we have the weight of the screw, the force applied due to the moment of the force here, due to the moment applied to the screw, and then we have the reactionary force of the thread. And notice that the angle between the weight, which is the vertical, and the reactionary force is simply the lead angle plus the angle caused by the friction between the surface and the screw. And that's how we want to think about the general concept of a threaded screw, which is very similar to the concept of a wedge. And so that's where that's coming from. And that's how it's done. Welcome to my lecture online. Here's another typical example of a wedge problem. What we're trying to do here is drive a wedge into a wooden log, trying to split the log. And the question is, if we're applying a force of 720 pounds down on the wedge, which has an angle of 12 degrees, what will be the force against the wood in a horizontal direction? We know that the coefficient of static friction between the wedge and the wood is 0.3, which allows us to find the angle phi, which is the angle between the reaction force and the normal to the wedge. We can say that phi will be equal to the arctangent of the static friction. And with a calculator, we can find out what that's equal to. So that's 16.7 degrees. Phi equals 16.7 degrees, which now, when we do a summation of the forces involved, we have the 720-pound force pushing downward, we have the two reaction forces in this direction, And notice that if we add the 16.7 degrees to the 6 degrees, which is half of 12 degrees, which is the angle between the horizontal and the normal, we have an angle here together of 22.7 degrees, which allows us now to draw the sum of the three forces. We have the, let's put it over here, so we have the force driving down the wedge, we'll call that W, which is 720 pounds. It's synonymous to the weight of an object, but in this case it's the force driving the wedge. We have reaction force 1 coming this way, and reaction force 2 coming this way. And of course the three forces add together should add up to 0. So this is reaction force R2, this is reaction force R1. Then we also realize that if we divide this in half, we draw this into a sum of two right triangles, that here the horizontal line here represents the force pushing against the one on the side. So that's really what we're looking for. We're looking for this F right here. So what we need to do is we need to find this angle, which is the angle of the horizontal relative to the reaction force, which is this angle right here. We know this angle is equal to 22.7 degrees. Here's the full force of the full magnitude of the force that's applied to the wedge. So if we take half of that, we have a force of 360 pounds. And then we have this angle of 22.7 degrees, which allows us to find F, because now we have a relationship between the adjacent side, the opposite side, and the angle. We can now say that the tangent of 22.7 degrees is equal to the ratio of the opposite side divided by the adjacent side. In this case, the opposite side is a half of the force applied to the wedge, 360 pounds, and the adjacent side would be F, which is what we're looking for. And that allows us to solve for the force. That way we can say that F is equal to 360 pounds divided by the tangent of 22.7 degrees. 360 divided by 22.7, take the tangent of that, and we have a force of 861 pounds. So F equals 861 pounds. So now you can see that by driving a wedge into a piece of wood like this, trying to split it, when we apply this force right here based upon the coefficient of static friction and the angle of the wedge, we apply a force horizontally against the wood, splitting it apart of 861 pounds to the right, and of course an equal and opposite force to the left as well, 861 pounds to the left. And that's how it's done.
Distributed forces, center of mass, center of gravity, and centroids. Wmec-Civ 1001 week 6 less. Copyright statement. This 172.24.191.117 McGet under. Contents. Center of mass. Application. Center of mass cm. Cm is a point around which the mass of an object is equally distributed. Can you guess the cm of the following distributed objects? Assume that the mass is uniformly distributed in each object shown. Hint. Think about the given definition. B, C, E, D, D. Center. What can we learn about the cm just from the previous activity, looking at these shapes? Center of mass depends on the shape of the object. In some shapes, the cm point is outside the body of the object. The cm is the point around which the object spins in a uniform constant gravitational field. For a non-uniform field, because gravity varies across the body of the object, it spins around its center of gravity cg. We'll compare the difference between cm and cg. 0. Center of mass. M, 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 x, m. Center of mass. For extended objects, the sum goes to an integral. dd. We break up an extended shape into infinitesimal masses and sum them up. As shown. Center of gravity. Definition. Center of gravity. R sub cg equals numerator, cap delta cap w sub 1, r sub 1 plus cap delta cap w sub 2, r sub 2 plus cap delta cap w sub 3, r sub 3. Note that delta ww, E and ww are magnitudes of weight forces. In general, center of gravity cg. The cg is calculated similarly to cm. The only difference is that the terms in the sum is also weighted with respect to the gravitational acceleration at each mass. Notice that when the gravitational acceleration GGII has the same value at every mass location, this reduces to the cm. All GGII cancels. This happens in a uniform gravitational field or in free space. CG only matters if there is a significant variation of gravitational field across the object. Because gravitational field varies very little close to the surface of the Earth, we never need to worry about it and use the cm instead, unless we are dealing with objects near black holes or other celestial objects. CG might matter when building skyscrapers. 3-dimensional center of gravity CG. Centroid of 2D and 1D objects. Introduction. Center of gravity of 2D or 1D body. Left figure, a generically shaped plate in the xy plane. The location of the center of gravity. Right figure, the location of an infinitesimally small portion of the plate. Left figure, a generically shaped wire in the xy plane. The location of the center of gravity. Right figure, the location of an infinitesimally small portion of the wire. Center of gravity of a wire. CG and CA are related. If the gravitational acceleration and the density are constants, then we can derive CV from CG as follows. Replace them with the product of density and volume R. VV, where V equals quadruple A, for some constant thickness, AA, and area, AA, dot, since R and AA are constants, they cancels from the equation. RRCC, CC, equals R sub cm equals numerator, sum from I, equals 1 to n of m sub I, right pointing arrow, integral dd, where AA, E is the ith area element and AA equals n area summation E equals 1 n n. AA, E is the total area, T, and continuous form, mean average value. F bar equals numerator, integral from a to b of f of x, dx and numerator over denominator b minus a, and denominator. Rectangle. F bar equals numerator, sum from I, equals 1 to, e.g. for equal steps. Centroids and first moments of areas and lines. Left figure, a generically shaped plate in the xy plane. The location of the centroid of the area. Right figure, the location of an infinitesimally small portion of the plate. Centroid of a line. Left figure, a generically shaped plate in the xy plane. The location of the centroid of the area. Right figure, the location of an infinitesimally small portion of the plate. X equals cap q sub y over cap a. Mean pointer centroid, y equals. Left figure, a generically shaped line in the xy plane. The location of the centroid of a line. Right figure, the location of an infinitesimally small portion of the line. XXLL. X represents axis here. First moments of areas and lines. First moments of areas and lines. Centroids of common shapes of areas. Composite plates and areas. The location of the center of gravity G of a composite plate can be determined from the centers of gravity G1, G2 of the component plates. The location of the center of gravity G of a composite plate can be determined from the centers of gravity G1, G2 of the component plates. Composite area. Centroids of common shapes of lines. Location of centroids for these common shapes of lines. Arc, circular arc, semicircular arc, and arc of a circle. The x-axis is the dividing line between the triangle and the rectangle. The y-axis is the left side of the rectangle. For the plane area shown, determine the first moments with respect to the x and y axes and the location of the centroid. The x-axis is the dividing line between the triangle and the rectangle. The y-axis is the left side of the rectangle. Strategy. Divide the area into a triangle, rectangle, and semicircle with a circular cutout. Determine the centroid of each smaller area with respect to the axes. Find the total area and first moments of the triangle, rectangle, and semicircle. Subtract the area and first moment of the circular cutout. Compute the coordinates of the area centroid by dividing the first moments by the total area. Modeling. Determine the dimensions and centroids for each of the basic shapes, rectangle, triangle, semicircle, circle. Dash. Find the total area and first moments of the triangle, rectangle, and semicircle. Subtract the area and first moment of the circular cutout. Analysis. Compute the coordinates of the area centroid by dividing the first moments by the total area. Cap x equals 54.8 millimeters. Rectangle. X equals 54.8 millimeters. Cap y equals 36.6 millimeters. Rectangle. E equals 36.6 millimeters. Reflect and think. Given that the lower portion of the shape has more area to the left and that the upper portion has a hole, the location of the centroid seems reasonable upon visual inspection. Centroid for volume CV. CG and CV are related. If the gravitational acceleration and the density are constants, then we can derive CV from CG as follows. Replace them with the product of density and volume R. VV. Dot. Since R is constant, it cancels from this equation. RRCC. CC. Equals. R sub cm equals numerator, sum from I, equals 1 to n of m sub I, r sub I, and summation n numerator, over denominator, sum from I, equals 1 to n of m sub I, and denominator, goes to numerator, integral of r dm and integral n numerator, over denominator, integral of dm and denominator. Right pointing arrow. RRDD. Integral dd. Where, VV, E is the ith volume element and V equals, n area summation E equals 1 n n. VV, E is the total volume, m, V. Centroid and first moment of volume. Centroids and volumes of common 3D shapes. Centroids of common shapes and volumes. Centroids of common shapes and volumes. CG of composite bodies. CV of composite bodies. Locate the center of gravity of the steel machine element. The diameter of each hole is 1 centimeter. Sample problem 5.12. Where do we expect the centroid to be? By inspection, you should expect XX and ZZ to be considerably less than 1/2 2.5 centimeters and 1/2 4.5 centimeters respectively, and YY to be slightly less in magnitude than 1/2 2 centimeters. Thus, as a rough visual check, these are the results we expect. 39. Strategy. Form the machine element from a rectangular parallelepiped and a quarter cylinder and then subtracting two 1 cm diameter cylinders. Modeling. Analysis. Cap x equals 0.577 centimeters. Rectangle. X equals 0.577 centimeters. Cap y equals minus 0.955 centimeters. Rectangle. E equals minus 0.955 centimeters. Cap z equals 1.618 centimeters. Z equals 1.618 centimeters. Sample problem 5.12. Reflect and think. By inspection, you should expect xx and zz to be considerably less than 1/2 2.5 centimeters and 1/2 4.5 centimeters respectively, and yy to be slightly less in magnitude than 1/2 2 centimeters. Thus, as a rough visual check, these are the results we expect. 43. Application of centroid. Loaded beams. Distributed loads on beams. A distributed load can be replaced with a concentrated load of magnitude equal to the area under the load curve and a line of action passing through the centroid of the load area. A simply supported beam, with roller at point A and pin at point B, of length 6 meters supports a distributed load that is 150 N per meter at point A and increases linearly to 450 N per meter at point B. A beam supports a distributed load as shown. Determine the equivalent concentrated load and the reactions of the supports. A simply supported beam, with roller at point A and pin at point B, of length 6 meters supports a distributed load that is 150 N per meter at point A and increases linearly to 450 N per meter at point B. Strategy. The magnitude of the concentrated load is equal to the total load of the area under the load curve. The line of action of the concentrated load passes through the centroid of the area under the load curve. Determine the support reactions by A. Drawing the free body diagram for the beam and B. Applying the conditions of equilibrium. The area under the load is divided into two triangles having a common side. Modeling and analysis. The magnitude of the concentrated load is equal to the total load of the area under the load curve. F equals 18.0 kilonewtons. The line of action of the concentrated load passes through the centroid of the area under the curve. The area under the load is divided into two triangles having a common side. X equals 3.5 meters. C. Vacuum approximately 1, Walpole approximately 1, locals approximately 1, temp MSOTW 9_temp0.jpg. Determine the support reactions by applying the equilibrium conditions. For example, successively sum the moments about the two supports. By equals 10.5 kilonewtons. I equals 7.5 kilonewtons. Bx equals 0. And by summing forces in the x direction. References. Vector Mechanics for Engineers Statics Dynamics, 12 edition, 2019. Ferdinand P.
Let's look at this problem. We have this composite area, and we need to determine its centroid x bar and y bar. And because this composite area is symmetric about the y-axis, therefore the centroid location must be on the y-axis. And we know that for any point that is on the y-axis, the x-coordinate is 0. Therefore, in this case, we can already tell that x bar equals to 0. All we need to do is to calculate y bar, which equals to summation y tutor a divided by summation a. So what does this equation mean? We can tell that this composite area is made up by 4 component areas. So we will have area 1 here, area 2 here, area 3, and lastly area 4. So for each of them, we need to calculate their its area, and also we need to determine its own centroid y location, y tutor. So which means that for area number 1, its own centroid is here at the geometric center of this rectangle, and this much is the y tutor 1. So we need to determine the y tutor for each of the component areas and then do the calculation to determine y bar for the entire composite area. So for this type of problem, it's easier to set up a table because we have 4 component areas. So we're going to have area number 1, 2, 3, 4 right here. And for the first column, we're going to calculate their individual areas with a unit of millimeter squared. So for area number 1 and 2, they are the same. So they have height of 100 millimeter with width of 20 millimeter. So that is 20 times 100, 2,000 millimeter. Area number 3, we will have a length of 200 millimeter and a height of 20. So 200 times 20, that is 4,000 millimeter squared. And for area number 4, the vertical one, we have height of 260 and width of 20. So 20 times 260, that is 5,200 millimeter squared. So that's the first thing. And then for the next column, we're going to calculate y tutor location for each of these component areas. So for area 1, we know that from here to here, that is 260 plus 20, that is 280. And from here to here, that is half of the height of area number 1, which is half of 100, which is 50. Therefore, y1 tutor equals to 280 minus 50. That is going to be, so actually, it should be, from here to here is also 50. So 280 minus 50, so that's going to be 230, which is the same for area number 2. So 230 here and 230 here. Area number 3 is going to be 280 minus half of its height, because its own centroid location is here. So 280 minus half of 20, which is 10. 280 minus 10, 270. And lastly, for area number 4, its own central location is here. So this is its y tutor location, y tutor coordinate, and that is 260 over 2, so 130. So that's the next column. For the next column, remember we need to calculate y tutor multiplied by a. It has a unit of millimeter to the third power, which is actually not very important. So we're going to take these two numbers and calculate their product. So 2,000 times 230, so that's going to be 460, 000. Same thing, 460, 000. And then we have 1080, 000, 676, 000. So what's next is to add the first column and the third column together. So for the first column, we're adding all the component areas together to get the total area. That is 2,000 plus 2,000 plus etc. etc. So that is 13200. And then we're going to add all these together as well. And that equals to 2676000 millimeter. Okay, so as you can tell, our y bar equals to the summation of y tutor a over the summation of a, which equals to this number 2676000 divided by this number 13200. And eventually that equals to 202.7 in the unit of millimeter. Therefore, the central location of the composite area equals to 0, that is x bar, 202.7 millimeter. So we can try to mark it on our sketch. So 202.7 is probably here. And that is the central location. In this video, we will focus on how to determine the centroid of an area, which is the geometric center of an area. From the previous video, we learned how to theoretically determine the location of the center of gravity for a rigid body with respect to a given coordinate system, x bar, y bar, and z bar. And we also know that weight equals to mass times g, which is the gravitational acceleration, and for the general near-Earth situation, it can be considered as a constant, about 9.81 meter per second squared. Therefore, the constant g can be cancelled out from the numerator and the denominator of this equation, and this new set of formulas now represent the coordinates of the center of mass for the rigid body. In this case, the center of gravity is the same as the center of mass. And we also know that mass equals to density rho times the volume. And if the rigid body has uniform density, then density rho can also be cancelled out from the numerator and the denominator of the equation. And now this new set of formulas represent the coordinates of the centroid of volume for this rigid body. Note that centroid means a geometric center. And in this case, the center of gravity, the center of mass, and the centroid of the volume are all the same point. And if the volume has a uniform thickness, then we can further reduce the situation from 3D to 2-dimensional and cancel out the thickness from this equation. And now we have coordinates for the centroid of an area. And sometimes we can even further reduce the situation by cancelling out the constant width of an area and get the coordinates for the centroid of a line. The line could be either straight or curved. Since centroid is the geometric center of a volume or shape, if the volume or shape has any axis of symmetry, then centroid must be on this axis of symmetry. Therefore, we can easily determine the centroid location of several common symmetrical shapes such as a cube, a circle, a rectangle, or a straight line. This can be used to help find the centroid for other unsymmetrical volume or shape. So let's look at this example, finding the centroid location for a right triangle with base of b and height of h. I will demonstrate this problem using two different approaches. First of all, we need to put this triangle into an xy coordinate system so that we can apply these two equations to find the centroid location. Since in these two equations, x and y represent the coordinates of an arbitrary point xy in this triangle, let's define a differential element at this location with sides of dx and dy. Therefore, the area of the differential element dA equals to dx times dy. Also, it is helpful to know the equation for this line, which is y equals to h over b times x, as we learned from linear functions probably in pre-calculus class. This is helpful because we will use this as the upper limit when we integrate along the y direction. Therefore, first we calculate for x bar. The numerator is an integration of x times dA integrated along the y-axis from 0 to the line h over bx and along the x-axis from 0 to b. And we get 1/3 hb squared. And we do the same thing with the denominator, which is 1/2 h times b. You might notice this is simply the area of the triangle, 1/2 height times the base. That is correct. The denominator in this formula is simply the total area. Therefore, x bar is calculated to be 2/3 times b. And then we do the same thing for the y bar. The denominator is, of course, still the total area, 1/2 h times b, but we need to integrate y dA, and eventually we get y bar equals to 1/3 h. This is the first approach. However, integration with two variables can sometimes be difficult. Therefore, let's look at a second approach in which we only need to integrate with one variable. So we have the same red triangle put in the xy coordinate system, but this time we choose a vertical strip of width dx instead of a little square to be our differential element. The height of this strip is determined by the y coordinate of this point, which is h over b times x, as we determined earlier from the equation of this line. Now, in these equations, as you can see, x and y are replaced by x tutor and y tutor. This is because now my differential element can no longer represent a particle. Therefore, in these two equations, x tutor and y tutor represent the coordinates of the centroid location of the differential element, which in this case is a rectangle, and we know that its centroid is right here at the center. And we can tell that x tutor equals to x, and dA equals to the area of the rectangle, which is the height, h over b times x, times the width, which is dx. We plug these into the first equation. Therefore, x bar equals to 2/3 b, just like we got using the first approach. But here, as you can see, we only need to integrate over one variable, x. To find y bar, we do the same thing, but use a horizontal strip instead. And again, we get the same result. Y bar is 1/3 h. So it is up to you to decide what is the best method to use. As you can see, choosing the differential element cleverly can greatly simplify your calculation. Now we mark the centroid position on the triangle. And as you can see, it is located at 1/3 location to either side. Actually, if you recall, we used this conclusion before when replacing a linearly distributed loading, the one that shapes like a triangle, with a concentrated load. The centroid locations for common shapes have long been summarized and can be easily found online or in engineering textbook or handbooks. For example, here is a screenshot of a Wikipedia page on centroids. You might find this information very useful.
Real life insurance really helps.
Pulleys are one of the... Hey, it's me, Destin. Welcome back to Smarter Every Day. It's time for the pulley episode. These are like my favorite things in the whole world. I bought this one. It looks like it goes to a boat or something like that. Pulleys are one of these things that everybody knows about. They know that somehow a pulley will give you mechanical advantage, but people don't really understand it. We all pretend like we do, but the person that really shows up and is really clever and they arrange it in a perfect way and they just make things work, that's like the smart person that everybody wants to be. So today on Smarter Every Day, we're gonna make a video about pulleys and we're gonna slowly walk through how they work. And specifically, I want to introduce you to my favorite type of pulley. It's called a snatch block. They're really fancy. They can do tricks. Okay, let's start by picking up these center blocks. My kids are gonna show you how to pick up blocks, right? If you have to pick something up, you have to pick up all of the weight of the thing and, whether you know it or not, all of the weight of you. How you doing? Good? You can put it back down? How hard was that? Not that bad? The magic of a pulley is really the magic of a rope, because a rope is always in tension. You can't push a rope. If you pull on this side of the rope, that force transfers all the way through the pulley. So you basically can redirect a force. That is the primary function of a pulley, redirecting force. It's pretty good. How was it?
Hard.
The pulley changes the direction of your body weight. So you can use your own body weight to help you pick something up. Very good. Was that hard?
Not as hard, not as hard.
Not as hard as what?
Just picking it up.
Okay, so it's easier to pick it up with the pulley because you can kind of lean into it, right? So this is the part that starts to confuse people. If you can change the way the pulleys are arranged, you can make it even easier to pick this up. Do you want the normal pulley or the snatch block? Snatch block. There you go. Go for it. So you split it apart. Don't cut your finger off there. There you go. So this is the magic of a snatch block. We can put a pulley in any place, anytime, as long as there's a rope, and a snatch block is big enough for the rope. This is the part where when you see it happen, you're like, oh yeah, of course it's easier because of pulleys. But if you don't stop and think, you won't really understand what's happening. So slowly pull. Is it really easy this time?
It's a lot more easy.
A lot easier. Okay, so this is what's happening. The tension in the rope right here is being redirected by this pulley because that's what pulleys do. They redirect force. But down here with the snatch block, we're doing the same thing. We're redirecting the force. But you have tension in the rope and tension in the rope. So all you do is you put tension in a rope somewhere, and then you add up as many ropes as possible on the thing, and that's how you get mechanical advantage. So in this case, how much force is on the cinder blocks? Do you know? 2 times the tension. I don't know about you, but I understand things a lot better if I can work with it with my hands. So I 3D printed a bunch of pulleys and snatch blocks, and we're gonna rig these things up and generate a model of how we were picking up those cinder blocks. When I pull on this rope, that tension transmits itself all the way through the rope to the very end. Wherever the rope is, there's also tension. If I pull here, think about the word pulley. It pulls on the rope on the other side of the pulley, right there. That pulls on the rope there at the bottom, which then pulls on the rope on the other side of that pulley, which ultimately pulls against that hook at the very end. All of the ropes are in tension. Now, if you look down there at the cinder block, you'll notice that there are 2 arrows pulling up on that pulley. That's why we get twice the force on the cinder blocks. But what if we want to pull harder? Can we just add more ropes and tension? Yes, we can, using this. It's basically a double pulley. Some people call this a block and tackle. Instead of 2 ropes pulling down here, we get 4. Just a little bit of force here. Even with my pinky finger, that's like 10 pounds of force by just barely pulling at all. This is the same number of ropes and like pulleys and everything. It's just flattened out so we can see what's going on. So I've got a scale. I'm going to attach a scale to the input of the rope. And remember, if we put input tension, that tension goes all the way through. So as I pull here, I have 1, 2, 3, 4 ropes connected to the thing we're pulling. So if I put 2 pounds here, look at that. I get 8 pounds on the output. That's awesome. I'm getting 4 times the force, but I'm only moving it 1/4 as far. How far do you think we can go with this? You think we can double it again? So now we have 2 blocks with 4 pulleys each, which if you count all those up, 1, 2, 3, 4, 5, 6, 7, 8, we have 8 ropes in tension on that block. So as I pull here, look at this. That's nuts. That is a little bit of force and a lot of output. That is some serious mechanical advantage. Look at this though. The ropes over close to me are moving a lot, but the ones over near you aren't moving as much. Let's break this thing apart again and see if we can understand what's happening. This is so awesome. Oh man, that's a great shot. Okay, so here's what we got. We've got 1 input pulley. Let's count up the tension again. 1, 2, 3, 4, 5, 6, 7, 8. I put 2 pounds here on the input. That is a lot of force on the output. Remember on the block and tackle, the ropes were moving at different rates. Well, think about this. On this side over here, that rope is tied up there. It's not going to move. On this side, I'm pulling the rope. It has to move as much as I pull it. And the same is true for this one because it's just redirecting that string. But after that, everything is affected by how much this moves. So just playing around with it here, you can see that these ropes move a whole lot more than that one over there that doesn't move at all. There's a lot going on here. Now, this is the sort of thing that, yes, you can probably explain it with words, but if you have a fundamental understanding of how this stuff works and you just know how to use it to your advantage, you can get yourself out of some really interesting situations. For example, the other day the drive shaft broke on my buddy Jeremy's truck and we had to figure out how to get his truck up onto a flatbed trailer without a winch. Snatch block. We rigged up a pulley system so that we could pull his entire truck up onto the trailer using only ratchet straps. We figured it out, but because we were trading force for distance, it was taking forever. That's when a nice guy named Jeff showed up. He drove up, offered to help, and instantly understood our pulley system and knew what to do with his truck. We disconnected one of the ratchets, put Jeff's truck in its place, and pulled his truck up until the rope hit the trailer. One thing I love about Alabama is nice people like Jeff just stop and help you, and they instantly know what's going on. For example, watch how quickly Jeff figures out all the mechanics once I tell him we have an extra snatch block. Oh, I'm so excited. We're going to do a double snatch block. Oh, this is great. I'm going to put that one there. Yeah. I'm gonna level with you. Jeff is the kind of guy I want to be when I grow up. Watch how he just picks up the snatch block and starts working. He just knows what to do. Also, his hands are just amazing. Watch this man work.
Snatch block engaged. How many snatch blocks you got?
Oh, about 5.
Dude, I'm an amateur. I only got 2.
I got a triple.
You got a triple? Like a
triple, yeah.
A block and tackle?
Yeah.
Oh, dude, that's a thing of beauty, my friend. Any day you can use a snatch block is a good day.
So yeah, snatch blocks can get you out of a hairy situation. Knowing how to use them can help you make friends, and they can also be a ton of fun. Zip lines are basically just snatch blocks. You have the ability to break apart the pulley, and you can insert a cable into it without having to disconnect the cable from either end. That's essentially the definition of a snatch block, a pulley where you can insert a line without having to take apart your line from whatever it's hooked to. Snatch blocks are amazing. Where else can you get amazing views of the rainforest canopy like this without having a snatch block? Look at that. Sit. That's awesome.
Okay, so you can't do a video about snatch blocks without getting the Jeep stuck, so let's go do that. Let's say you got the Jeep stuck. You might be tempted to find the nearest tree, pull the winch out, and pull the cable directly to that tree. What do you think, Jeremy? Winch, way to go? Winch is... Oh, we're gonna snatch block this back.
Snatch block.
All right, you got the winch, right? I got the winch. Okay, here we go. Oh, that's scary. That's a lot of force, dude. That's good. Dude, that's a lot of force, man. Thoughts?
All right, man. Well, this has the same mechanical advantage, but it does it a different way. You remember we add up the tension on these ropes, and we have 1 + 1 is equal to 2. But if we have 2 + 2 is equal to 4, and 4 + 4 is equal to 8, we can come up with an 8-to-1 mechanical advantage just like that with less pulleys. This is fascinating, and one of the first people to come up with this concept is a guy named Archimedes. To learn more about Archimedes, I went to my local library and got a book by a man named Plutarch who mentions an interaction between Archimedes and King Hero of Syracuse. It's a really interesting story, but it's going to be even better if I tell it to you with this flannel board. So it goes like this. Archimedes writes a letter to King Hero of Syracuse, and he's like, yo, King Hero, I'm really good with pulleys and stuff. And Hero's like, why don't you prove it? Archimedes is like, well, I will if you give me a warship. And King Hero's like, yo, dog, here's your warship. And then Archimedes is like, yo, dog, I hear that you like pulleys. I got pulleys on pulleys on pulleys. And then Archimedes does something amazing. Under his own physical strength, he pulls an entire warship out of the dock, which totally impresses the king because that's what happens when you know how to use pulleys. You impress people. So people have been using pulleys and snatch blocks for thousands of years, and they've been impressed all the way back in the day with Archimedes. But they're going to be used for thousands more. That's why you need to know how to use a snatch block. Don't take my word for it, though. I'll let veteran astronaut Commander Chris Hadfield explain it from his point of view.
The biggest difference between being on Earth and being in space is that you're weightless. And when you're floating around weightless, like on the space shuttle, it's really hard to get leverage. You can't dig your feet in. You can't use the weight of things to hold them in place. So having a way to hook on one end and hook on the other end and apply a steadily increasing force is really important. And that's why on board the space shuttle, we have snatch blocks. They're part of normal equipment. In fact, there's a special stowage block for them that contains a couple. And they get used pretty regularly, both inside the ship and even outside on a spacewalk.
You're in a problem. You have a load. You have to pick it up. What do you do? Snatch block! It's kind of funny when it doesn't work. And get your team out of the situation. Snatch block. Snatch blocks are amazing. I want to tell you something else that's amazing, and that is the sponsor for this video.
Test 2 revision questions. Friday the 28th of August 2020. 1. 11:01 a.m. Machine. A digger has a hydraulic piston BD to raise the digging arm. Calculate the forces on the base of the machine at A and B. 2. 3. Centroids. The Z-shaped wire is balanced on a pin. The diagonal length is 40 centimeters and the horizontal and vertical lengths are 20 centimeters. What is the value of x for which the wire can balance? Centroids. Calculate the first moments of area and the centroid of the following shape. 4. Friction. It takes 20 N to crack the nut at the base of this nutcracker. What force P is required to achieve this? The screw is a single thread of 1 centimeter radius and 3 millimeters pitch. Mu equals 0.3. 5. Internal force. Determine the internal reactions at A. There is a roller support at B and a pin joint at O. 6. Calculate the minimum force P required to move block B. 7. A 1 mm radius single threaded screw with pitch of 1 mm is used to hang a 10 kg mass. For what minimum static friction coefficient is the screw self-locking? B. Using your answer to part A, for a mass of 20 kg, what is the moment required to screw in the screw? Moment of inertia. Wmec-Civ 1001 week 7 lesson 1. Copyright. Lesson. In this lesson you will recap of first moment of area and rotational inertia. Understand why the second moment of area represents resistance against loading in case of uniform mass distribution. Understand how to calculate second moment of area. Recap. First moment of area and centroid. It is often calculated for x and y coordinates separately, e.g., y, x, y equals a e, y, e n aries a e equal n aries a e y e r int y d a integral d quadruple a equals q. Recap. Rotational inertia. Rotational inertia represents a quantity that tells us how hard it is to rotate, i.e. speed up, slow down, an object around a given axis. Example of the second moment. SS. Cis less than SS. Recall from rotational k that is the rotational inertia of the small mass m. Recap. Rotational inertia. The rotational inertia for a distributed set of small masses is given by based on the sum principle. 2. Center of mass cm. Rotational inertia. Objects are easiest to rotate around their cm axis because the mass distribution is closest to this axis of rotation in a given plane. Recap. Rotational inertia. Kappa equals kappa sub cm plus kappa md squared. Rectangle. If we want to rotate around a different axis which is parallel to the center of mass axis, then mass is distributed farther from the axis of rotation and the object becomes harder to rotate. Recall, we use the parallel axis theorem to calculate this new rotational inertia as follows. Cm axis. Parallel axis theorem. Center of mass rotational inertia. X. Measure of area distribution. Centroid. As far as the axis goes through the centroid, the second moment of area gives a good indication about the stability of the beam against loading. Here in the x direction for homogeneous materials. Uniform density. Rotational inertia and second moment of area. 2 equals IICCCC plus MMDD2. IICCCC equals AAR. RR2. AA. Second moment from the center of area axis. Center of mass rotational inertia. Cap I sub A equals cap I sub CA plus cap AD squared. Rectangle. Parallel axis theorem. For second moment of area. CA. Axis. Bending moment and area distribution. Bending moments explained intuitively. Zero mathematics video. Second moment of area. An alternate derivation. Distribution of material and internal forces. Second moment of area. Beam cross sections. Diagram. Engineering drawing. Description automatically generated. Diagram. Engineering drawing. Description automatically generated. Common shapes. Rectangular shaped shaded area in the first quadrant with base B, height h, and centroid at point C which is located at the intersection of the x and y axis. Triangular shaped shaded area with base B, height h, and centroid at point C which is located on the x axis. Circular shaped shaded area centered at the origin with radius r and centroid at point O. Semicircular shaped shaded area in the first and second quadrants, symmetric about the y-axis, centered at the origin with radius r and centroid at point C. Quarter circle shaped shaded area in the first quadrant with radius r and centroid at point C. Parallel axis theorem. As expected, the parallel axis theorem is used for second moment of area. Other definitions to know. A generic shaped figure is positioned in the xy plane. The area is positioned in the first quadrant with coordinates x, y. The area is located a distance r from the origin. The polar moment of inertia is an important parameter in problems involving cylindrical shafts and rotations of slabs. The polar moment of inertia is related to the rectangular moments of inertia. The polar second moment of area is used to describe resistance to torsion, y. Hint, notice that we are integrating area in all directions around a point on a plane, i.e. perpendicular axis of interest. Moment of inertia. 172.24.191.117 McData underscore volume 408 VOL4 graphics PowerPoint MH underscore DCM MH underscore DCM text edit projects MH037 year underscore 12 final files chap 09 CH09 underscore labeled underscore J. Find the moment of inertia of a circle with respect to a line tangent it. Moment of inertia. IIDDDD equals IIBBBB plus A add 2 equals. Cap I sub, superscript base, cap D, IIA, moment of inertia. Step 1, determine the moment of inertia for area 1. Step 2, determine the moment of inertia for area 2. Step 3, find the total moment of inertia about the x-axis. Step 4, repeat the same steps to find total moment about the y-axis. Y, AA1, 20, 60, 40, 20. Moment of inertia. 1, we need to find the centroid to be able to find the moment of inertia. 2, to find the moment of inertia of an object about the x-axis. Moment of inertia. From previous lecture slide, by using the reference point indicated in the figure, AA1, 60, 20, 20, Y, X, 20, 70, 20, 30, 20, 46. Moment of inertia. AA1, 20, 40, 20, 20, 20, 46, Y, X. Moment of inertia. Fill in the blanks. Y. Centroid of components. Mod of component. Parts. AA. XX. YY. IIXX. IIYY. DDXX. DDYY. AADDXX22. A at E22. IIXX plus A at E22. IIYY plus AADDXX22. Rect. Circle. Total. Moment of inertia. Fill in the blanks. Y. Centroid of components. Mod of component. Parts. AA. XX. YY. IIXX. IIYY. DDXX. DDYY. A at E22. IIYY plus AADDXX22. Rec. 15,000. 50. 75. 2.8125 times 10 to the 7. 1.25 times 10 to the 7. 0. 0. 0. 0. 2.8125 1.25 times 10 to the 7. Circle. 1,960. 50. Total. 50. Moment of inertia. Calculate the following for the object. I the centroid. E the moment of inertia about centroidal x-axis. E the moment of inertia about centroidal y-axis. 20. 20. 60. 60. Moment of inertia. Parts. AA. XX. YY. IIXX. II. DDXX. DD. AA. II. 4. 8. 1.51 times 10 to the parts. AA. XX. YY. AAXX. AAYY. Rec 1. 1,010. 4. 6. Rec. 1. 5. 10. Total. 2,800. 76,000. 76,000. XX. 20. 20. 60. 60. 1. 2. Moment of inertia. Calculate the following for the object. I the centroid. E the moment of inertia about centroidal x-axis. E the moment of inertia about centroidal y-axis. Moment of inertia. Parts. AA. XX. YY. II. D. D. AA. II. Rec. 1. 10. 40. 5. 0. 0. 8. Rec. 1. 5. 10. 4. 3. 6. 3. 1. 1. 6. Rec. 1. 5. 4. 6. 33. 1. 1. 6. Total. 4. 34. 3. 2. Parts. AA. XX. YY. AA. Rec. 1. 1,010. 6. 64,000. Rec. 2. 1,002. 5. 10. 6. 12. Rec. 1,200. 7. 6. 84. Total. 1. 1. XX equals 34 YY. 1. 2. Y. Normalize. Second moment of area. Other definitions to know. A generic shaped figure is positioned in the XY plane with area A. Rectangular strip parallel to the x-axis, straddling the y-axis with. Replace an area A that has moment of inertia with an equivalent thin strip that has the same moment of inertia. A generic shaped figure is positioned in the XY plane with area A. Rectangular strip parallel to the x-axis, straddling the y.
In this problem, we have an 80 kilogram crate that is simply standing on this moving cart on this inclined surface with a 15-degree angle with the horizon. And because the crate simply stands on the cart, it means that there's nothing else that keeps this crate from moving except for the frictional force between the surface of the crate and the cart. So we need to determine this acceleration. What is the maximum acceleration that the cart can have without causing the crate to move? It could be either tipping over or sliding relative to the cart. This is the same thing as asking what is the minimum acceleration A needed for the crate to start moving. We need to determine when that happens, when the motion happens, the relative motion of the crate with respect to the cart. Is it crate sliding relative to the cart or is it tipping over? The static friction coefficient is given between the crate and the cart. So let's use this example to illustrate typically how we deal with this kind of problem. This is, by the way, a translation problem. There's no rotation or general plane motion involved. So we start with drawing a free body diagram of the crate. So the gravitational center is given, the dimension of the crate is given as well. It is subjected to weight, which is mg, and also the normal force from the cart. Right now, we do not know exactly where this location of the normal force is. And because the cart moves up, therefore the relative impending motion of the crate with respect to the cart is down. So this is the direction of relative motion of the cart. Therefore, frictional force develops to prevent impending motion. Therefore, frictional force is up as well. So we need to determine the direction of the frictional force. That will greatly help with the analysis. You can tell that the frictional force is actually the only force that makes the crate to move uphill with the cart. If the frictional force is in the other direction, the crate will no doubt slide down. So now we have completed the free body diagram. Let's choose a coordinate system. Let's align our x and y coordinate system with the inclined surface and then perpendicular to it for convenience. And also we need to draw the kinetic diagram, which is basically drawing the MAG, which is in this direction along the inclined surface. This is the mass center or the gravitational center of the crate. So with this down, we can start writing our equations of motion. So let's write the first equation. Let's write resultant force along the y direction, which is again in this direction. And that equals to the normal force minus W times cosine 15 degree equals to 0. And this is n minus mg, which is 80 times 9.81 times cosine 15 degree equals to 0. Also, resultant force along the x direction, x is in this direction, equals to frictional force minus W sine 15 degree, which equals to frictional force minus 80 times 9.81 times sine 15 degree equals to MAG, which is 80 times AG. So now here we have two equations. Equation 1 and equation 2. Now, how many unknowns do we have? We have normal force, frictional force, and AG. So we have 3 unknowns, only 2 equations, obviously not enough to solve for all of our unknowns, even though we can actually solve for normal force here. So from the first equation, we can find out that normal force equals to 758.1 Newton. So now, in order to solve for the other 2 unknowns, we need one additional equation. So where do we get that? We can write different third equation based on the assumption we make. So if we make the assumption that, let's assume first, sliding occurs. This is when the crate slides relative to the cart, so the crate will slide down in this direction. If that happens, we will know that the frictional force between the crate and the cart has now reached the maximum static friction, which now can be evaluated by this equation, mu s times m. You cannot use this equation unless you know that the static friction has reached the maximum value. This is when sliding is about to occur. So mu s is given as 0.5 times normal force, which is solved earlier, 758.1. So this is our third equation. So from here, we can solve for frictional force to be 379 Newton. It's actually not important because it's the AG that we need. AG can then be solved from the second equation by substituting frictional force into it. Then AG equals to, in this case, 2.20 meter per second squared. This is not the final answer. This is the acceleration needed for sliding to occur. However, what if it's tipping over that occurs first? If that's the case, then frictional force no longer equals to mu s n. Remember, this equation can only be used when frictional force reaches limiting value when sliding is about to occur. So in this case, we cannot write this third equation. We need another third equation. Based on what we've learned back in statics, we know that when tipping over is about to occur, we actually know the location of normal force. Before, we wouldn't know the location of normal force, but now we know that the normal force location, it has to be placed at this corner. Let's call it point A. So with this specified location, now we can write our moment equation of motion. So if we summarize the moment about point G, which is the gravitational center, because we have translation, therefore the resultant moment about point G equals to 0. This is only true at point G. If you summarize the moment about any other point, the result is not 0. So this is only true for translation for moment about G, gravitational center. So in this case, if again we assume counterclockwise to be positive, then the frictional force is causing counterclockwise rotation with moment arm of 1.5 meter, and the normal force is causing clockwise rotation with a moment arm of 0.5 meter. And that equals to 0. And because we know what normal force is, from here we can solve for normal, so let me say that first. This is our third equation now. So now with 1, 2, and 3 equations, we can solve for frictional force to be 252.7 Newton. Similarly, substitute into the second equation, we can solve for AG to be 0.60 meter per second squared. So again, this is the maximum acceleration the car can have without causing the crate to tip over. Before I further analyze the situations, let me say that you can actually write an alternative moment equation. You can summarize the moment about point A. This is not 0. However, the resultant moment about point A, which equals to the moment caused by the weight, if we take counterclockwise to be positive, then this equals to W times sine 15 degree times 1.5 minus W times cosine 15 degree times 0.5. So that's the x component and that's the y component causing moment about point A. Normal force and frictional force pass through point A. They do not have moment about point A. And this equals to not 0, but the kinetic moment mk about point A, which equals to the moment caused by the kinetic force MAG about point A. MAG is causing clockwise rotation about point A, therefore this equals to negative m times AG times the moment arm of 1.5, because AG is placed at the gravitational center. Therefore, from this equation alone, actually, you can solve for AG, which will give you the same answer. So this is an alternative method. Either way, now we have evaluated the two acceleration. One is the acceleration that will cause sliding to occur. The other is the acceleration that will cause tipping over to occur. And if we compare them, we realize that the second situation only takes a smaller acceleration. Therefore, the final answer should be AG equals to 0.62 meter per second squared. And this is when tipping over occurs, because it takes smaller acceleration to cause tipping over. It is easier to cause tipping over. It is harder to cause relative sliding. So that's the final answer to this problem. So even after you have made the assumptions, have done the calculations, you still have to make a decision. In this problem,
Kinematics of particles. Wmec-Civ 1001. Week 7. Introduction. Kinematics. Study of the geometry of motion. Relates displacement, velocity, acceleration, and time without reference to the cause of motion. Kinetics. Study of the relations existing between the forces acting on a body, the mass of the body, and the motion of the body. Kinetics is used to predict the motion caused by given forces or to determine the forces required to produce a given motion. Ray square with forces acting upon it, drive force, aerodynamic downforce, and drag. Kinematics. Kinematic relationships are used to determine the trajectory of a snowboarder completing a jump, the orbital speed of a satellite, and accelerations during acrobatic flying. Introduction. Rectilinear motion. Position, velocity, and acceleration of a particle as it moves along a straight line. Curvilinear motion. Position, velocity, and acceleration of a particle as it moves along a curved line in 2 or 3 dimensions. Curvilinear motion. Zero-limbed. The velocity vector is tangent to the path and proportional to the change in position vector, i.e. proportional to displacement. VV increment RR. Curvilinear motion. Rectangular components of velocity and acceleration 1. Velocity vector. Acceleration vector. Graphical solutions 1. Null. Acceleration data from a head impact during a round of boxing. Graphical solutions 2. Given the VT curve, the AT curve is equal to the VT curve slope. Graphical solutions 3. Given the VT curve, the change in position between T1 and T2 is equal to the area under the VT curve between T1 and T2. Rectilinear motion, position, velocity and acceleration 3. From the definition of a derivative. Concept quiz 1. A. The velocity of a particle is always positive. B. The velocity of a particle is equal to the slope of the position time graph. C. If the position of a particle is 0, then the velocity must 0. D. If the velocity of a particle is 0, then its acceleration must be 0. Concept quiz 1. A. The velocity of a particle is always positive. B. The velocity of a particle is equal to the slope of the position time graph. C. If the position of a particle is 0, then the velocity must 0. D. If the velocity of a particle is 0, then its acceleration must be 0. Rectilinear motion, position, velocity and acceleration. V equals dx over dt equals 12t minus 3t squared. What are x, v, and at t equals 2s? At t equals 2s, x equals 16 meters, v equals vmax equals 12 meters per second, a equals 0. Dash. Note that vmax occurs when a equals 0, and that the slope of the velocity curve is 0 at this point. What are x, v, and at t equals 4s? At t equals 4s, x equals x max equals 32 meters, v equals 0, a equals minus 12. Sample problem. Determine velocity and elevation above ground at time t. Highest elevation reached by ball and corresponding time, and time when ball will hit the ground and corresponding velocity. Strategy. Acceleration is constant, so we can directly integrate twice to find vt and yt. Solve for t when velocity equals 0, time for maximum elevation, and evaluate corresponding altitude. Solve for t when altitude equals 0, time for ground impact, and evaluate corresponding velocity. Sample problem. Integrate twice to find vt and yt. V of t equals 10, m over s minus open paren 9.81, m over s squared, v vtt equals 10 milliseconds minus 9.81 milliseconds to dt. Y of t equals 20 meters plus open paren 10, m over s, close paren, t minus open paren 4.905, m over s squared, close paren, t squared. Rectangle. YYTT equals 20 meters plus 10 mstt minus 4.905 milliseconds to dt2. Sample problem. To find the highest elevation reached, first solve for t when velocity equals 0. T equals 1.019 s. Rectangle. TT equals 1.019 s. Y equals 25.1 meters. Rectangle. YY equals 25.1 meters. Sample problem. To find the velocity when the ball hits the ground, first solve for t when altitude equals 0, and then evaluate the velocity at that time. T equals minus 1.243 s open paren meaningless, close paren t equals 3.28 s. Rectangle. TT equals minus 1.243 s meaningless, TT equals 3.28 s. V equals minus 22.2 m over s. Rectangle. VV equals minus 22.2 milliseconds. Rectangular components of velocity and acceleration projectile motion. With initial conditions, integrating twice yields. Motion in horizontal direction is uniform. Motion in vertical direction is uniformly accelerated. Motion of projectile could be replaced by 2 independent rectilinear motions. X, Y. Sample problem 1. Sample problem 2. Given. Open paren a, close paren sub y equals minus 9.81 meters per second squared. Open paren a, close paren sub x equals 0 meters per second squared. Vertical motion, uniformly accelerated. Vy equals. V sub y equals open paren versus sub y, close paren sub 0 plus it versus sub y equals 90 minus 9.81 t, open paren 1, close paren y equals open paren versus sub y, close paren sub 0, t plus 1 half at squared, y equals 90 t minus 4.90 t squared, open paren 2, close paren versus sub y squared equals open paren versus sub y, close paren sub 0 squared plus 2y versus sub y squared equals 8100 minus 19.62 y open paren 3, close paren. 1y equals vy 0 t plus 1 2 at 2y equals 90 t minus 4.90 t2. 2by2 equals vyo2 plus 2y by2 equals 8100 minus 19.62 y3. X, y. Sample problem 2. Horizontal motion, uniformly accelerated. Choose positive x to the right as shown. X equals open paren versus sub x, close paren sub, 0 to the t, and subscript, x equals 155.9 t. Sample problem 3. Horizontal distance. Projectile strikes the ground at, y equals minus 150 meters. Substitute into equation 1 above. Solving for t, we take the positive root. Tt equals 19.91 s. Substitute t into equation 4. X equals 3100 millimeters. 0 equals 8100 minus 19.62 y. Maximum elevation above the ground equals 150 meters plus 413 meters equals 563 meters. Launch at 180 meters per second at an angle of 30 degrees from horizontal. Initial height is 150 meters above bottom surface, and acceleration is 9.81 meters per square second due to gravity. Sample problem 4. Because there is no air resistance, you can treat the vertical and horizontal motion separately and can immediately write down the algebraic equations of motion. If you did want to include air resistance, you must know the acceleration is a function of speed. You will see how to derive this in chapter 12, and then you need to use the basic kinematic relationships, separate variables, and integrate. Concept quiz 5. If you fire a projectile from 150 meters above the ground, CX problem 11.10, what launch angle will give you the greatest horizontal distance x? A launch angle of 45. B a launch angle less than 45. C a launch angle greater than 45. D it depends on the launch velocity. Concept quiz 5. If you fire a projectile from 150 meters above the ground, CX problem 11.10, what launch angle will give you the greatest horizontal distance x? A launch angle of 45. B a launch angle less than 45. C a launch angle greater than 45. D it depends on the launch velocity. Motion of several objects. Motion of several particles. Motion of several particles. Dependent motion. Block A is attached to a rope that goes up the stationary pulley CD, goes down to moving pulley EF which is attached to block B, and then goes back up to get affixed to the ceiling at G. The position of each block is its distance from the ceiling. Motion of several particles. Dependent motion. A rope comes down from the ceiling and passes through a moving pulley attached to block A. It then goes up to pass through a fixed pulley at the ceiling, then down to a moving pulley attached to block B, then up to a fixed pulley at the ceiling, and finally down again to block C. Sample problem 4. Group problem solving 8. Block lies on a horizontal surface, while block B moves up and down. A rope from the right side of it passes over a stationary pulley, passes through a pulley attached to block B, up to a stationary pulley, and back down to get attached to B again. Strategy. Sketch your system and choose coordinate system. Write out constraint equation. Differentiate the constraint equation to get velocity. Group problem solving 9. Sketch your system and choose coordinates. X underscore A is the horizontal distance from the first fixed pulley to block A. Y underscore B is the vertical distance from the same pulley block B. Differentiate the constraint equation to get velocity. X underscore A is the horizontal distance from the first fixed pulley to block A. Y underscore B is the vertical distance from the same pulley block B. Group problem solving 10. Block lies on a horizontal surface, while block B moves up and down. A rope from the right side of it passes over a stationary pulley, passes through a pulley attached to block B, up to a stationary pulley, and back down to get attached to B again. Reflect and think. Block lies on a horizontal surface, while block B moves up and down. A rope from the right side of it passes over a stationary pulley, passes through a pulley attached to block B, up to a stationary pulley, and back down to get attached to B again. References. Vector Mechanics for Engineers Statics Dynamics, 12th edition, 2019. Ferdinand P. Beer, E. Russell Johnson Jr., David F. Mazurek, Philip J. Cornwell, Brian P. Self, McGraw-Hill Relative motion. Wmec-Civ 1001 week. Copyright statement. This material. Motion relative to a frame in translation 1. Motion relative to a frame in translation 2. Motion of several particles. Relative motion. XXBB equals XXA plus XXBBAA. ABBAA equals AABB minus quadruple A equals. Relative acceleration of B with respect to A. Sample problem 1. Sample problem 1. Sample problem 2. Ball thrown upward from initial height 12 meters with initial upward velocity 18 meters per second with constant downward acceleration of 9.81 meters per square second due to gravity. Modeling and analysis. Sample problem 2. Modeling and analysis. Open elevator starting from initial height of 5 meters and moving upward at a constant velocity of 2 meters per second. Sample problem 3. When the ball hits the elevator, their positions are equal. T equals minus 0.39 s open paren meaningless, close paren T equals 3.65 s. Rectangle. A equals minus 0.39 s meaningless A equals 3.65 s. Substitute impact time into equations for position of elevator and relative velocity of ball with respect to elevator. When the ball hits the elevator, their positions are equal. YYE equals 12.3 meters. V sub, cap B linear divide cap E and subscript equals minus 19.81 m over s. Rectangle. VVBBE equals minus 19.81 milliseconds. Sample problem 4. Reflect and think. Concept quiz 3. Train A is going westward at 66 km per hour. Train B is going at 48 km per hour, 25 degrees north of east. A. Train A is going westward at 66 km per hour. Train B is going at 48 km per hour, 25 degrees north of east. B. 25 degrees north of east. C. 25 degrees south of west. D. Less than 25 degrees south of west. Concept quiz 3. Train A is going westward at 66 km per hour. Train B is going at 48 km per hour, 25 degrees north of east. A. Train A is going westward at 66 km per hour. Train B is going at 48 km per hour, 25 degrees north of east. B. 25 degrees north of east. C. 25 degrees south of west. D. Less than 25 degrees south of west. West. Sample problem 1. Determine the position, speed, and acceleration of car A at t equals 5s. Determine the position, speed, and acceleration of car B at t equals 5s. Using vectors equation 11.30, 11.32, and 11.33 or a graphical approach, determine the relative position, velocity, and acceleration. Sample problem 2. Define axes along the road. Given. Determine motion of automobile A. We have uniform motion for SO. At t equals 5s. AAA equals 0 VAA equals 10 kk SS right pointing arrow RAA equals 50 kk right pointing arrow. Sample problem 3. Determine motion of automobile B. We have uniform acceleration for B so. At t equals 5s. AB equals 1.2 kk SS2 down pointing arrow VBB equals 6 kk SS down pointing arrow RBB equals 20 kk down pointing arrow. Sample problem 4. AB equals 1.2 kk SS2 down pointing arrow VBB equals 6 kk SS down pointing arrow RBB equals 20 kk down pointing arrow. Right triangle with horizontal position of A being the bottom side at 50 meters, vertical position of B being the left side at 20 meters, and relative position of B with respect to A being the hypotenuse. A equals 21.8 ring operator. Right triangle with horizontal velocity of A being the top side at 10 meters per second, vertical velocity of B being the left side at minus 6 meters per second, and relative velocity of B with respect to A being the hypotenuse. BB equals 31.0 ring operator. Relative acceleration of B with respect to A is just the same as acceleration of B of minus 1.2 meters per square second. Or we can solve the problems using vectors to obtain equivalent results. Physically, a rider in car A would see car B traveling south and west. Sample problem 5. References. Vector Mechanics for Engineers Statics Dynamics.
This lecture covers the analysis of statically determinate trusses using the method of sections. Please review the previous lectures before continuing with the method of joints. Consider this statically determinate truss. Suppose we want to calculate the force in member CD only, without analyzing the entire structure. We can do this by cutting through a few truss members in order to split the structure in two parts. When we cut a truss member, we expose its internal force. In this case, since we have cut through 3 members, we've exposed 3 member forces. We know that when a truss is in the state of equilibrium, the equilibrium equations are satisfied for the entire structure, and for any isolated part of it. So in this case, we can argue that since the entire truss is in the state of equilibrium, these two parts must also be in equilibrium. That is, the 3 equilibrium equations must be satisfied for each part. To compute the force in member CD, we only need to consider one of the diagrams. We don't need both of them to do the calculations. Let's consider this diagram, for which we can write three equations in terms of FCD, FCH, and FGH. The equations are, the sum of the forces in the x direction must be 0. The sum of the forces in the y direction must be 0. The sum of the moments, say about point H, must be 0. We can solve these equations for the unknown member forces. If we want to calculate FCD only, we can use the third equation. It gives FCD equals negative 36K. If necessary, we can use the other equations to determine the other unknown forces. The second equation gives FCH equals negative 50.9K. Then we can use the first equation to get FGH. Note for this particular problem, we did not need to know the support reactions in order to determine the force in member CD. But in some other cases, we may have to calculate the support reactions before we could apply the method of section to solve the problem. For example, suppose we want to calculate the tension force in member BC. We cut through members FG, FC, and BC, dividing the truss into two parts. This leads to a total of 5 unknown forces for the left diagram. There are 3 unknown member forces and 2 unknown support reactions. And the right diagram is having a total of 4 unknowns. But we can only write 3 equilibrium equations for each part, so we end up with more unknowns than equations, which means we cannot solve the equations for the unknowns. Therefore, it is good practice to calculate the support reactions before splitting the trusses into 2 parts. We can calculate the support reactions by writing the static equilibrium equations for the entire truss. The sum of the forces in the x direction must be 0. The sum of the forces in the y direction must be 0. The sum of the moments about point A must be 0. Solving these equations for the unknowns, we get. Knowing the support reactions, we are now ready to apply the method of sections for determining the force in member BC. We cut the truss like this. Now we can use the equilibrium equations to calculate the unknown member forces. Since we are interested in determining FBC only, we can calculate that force by writing the moment equilibrium equation about point F. Solving this equation for FBC, we get FBC equals negative 36K. Let's summarize what we've learned so far. The method of sections is suitable for calculating a few member forces without needing to analyze the entire truss. 4 main steps are involved in using this method. 1. We calculate the support reactions for the truss. 2. We cut the truss through the target member and a few other members in order to divide the structure into 2 separate parts. This exposes the internal forces in the cut members. Hence, 1 force per cut member is exposed. 3. We draw the free body diagram for one of the parts, showing the support reactions and the exposed member forces and relevant distances and angles on the diagram. 4. We write and solve the equilibrium equations for the free body diagram in order to determine the unknown forces. Let's apply this procedure to solve another problem. Consider this statically determinate truss. Suppose we wish to calculate the force in member EF. We start by calculating the support reactions for the entire truss. Here's the free body diagram of the system, for which we can write 3 equilibrium equations. Solving these equations for the unknowns, we get the values for BY, AY, and AX. Let's cut the truss horizontally, like this. The cut divides the truss into 2 separate parts, exposing 3 member forces, one of which is our target force. We can use either of these 2 diagrams to calculate the target force. Let's take the lower free body diagram. Note the angle that FEF makes with the horizontal axis. We have labeled the angle alpha. We need to know the angle in order to calculate the unknowns. We can determine alpha using simple trigonometry. Tangent of alpha equals 2 over 5. Hence alpha equals 21.8 degrees. To determine FEF, we can set the sum of the forces in the x direction to 0. Solving this equation for the unknown force, we get. In summary, using the method of sections, we can calculate the force in a member without needing to analyze the entire truss. For most statically determinate trusses, we can easily apply the method of sections to calculate member forces. However, there are a few cases that you need to be aware of when dealing with this method. Case 1. How to cut a K-truss for calculating a member force. Case 2. What if the number of unknowns is more than the number of equations? Case 3. When using the method of sections,